Well, good day. I'm so sorry. I look haggard today. Happy Valentine's, everybody. Okay. Now, our topic is actually all about what is propositional logic, which pertains to the logical statements. As I'll begin to deal with the connectives and as well as the truth table in different videos. However, there will be a part of that here already. Now, what is propositional logic? As what I have mentioned to you then before that, a propositional logic is definitely a sentential logic, a branch of formal logic that focuses on propositions like simple declarative statements that are either true or false. And these propositions can be combined and manipulated using logical connectives, which allow for more complex logical expressions. So in this particular field class for propositional logic, we're dealing with a statement if it is either true or false, and we are trying to quantify them if where is it really belong. Now, a proposition is a statement that asserts that is either true or false, but not both. So, example, the sky is blue. Is it true or false? So that therefore that is true. And 2 plus 2 is equals to 4. That is true, right? And it is raining. It can be quantified as true or false as well. Now, for this type of proposition, just take note that there will be a simple proposition. When we say simple proposition, that is referring to one statement. That is a statement that expresses a single idea or fact to be either true or false. For example, the earth is round. So it is a simple proposition because it represents one clear claim that can be verified as true or false then. And that is really so simple, right? Then we also have a compound proposition. When we say compound proposition, that is not dealing with one statement only. This is actually a combination of two or more simple proposition using logical connectives like and or not. So we do have logical connectives that we'll begin to analyze in the future. And for instance, here then the Earth is round and the sky is blue. So we have the connectives. We're able to use that one, which is the and. It is a compound proposition because it connects two simple proposition. The Earth is round and also the sky is blue. They are separate. There will be statement one and statement two that is being connected or combined through a logical connector. Now, a logical connector right there is the and, making the whole statement true only if both individuals' propositions are true. It depends on the situations then. Okay. Now, why study propositional logic? This is actually important because it will provide a framework for reasoning, which is essential across various disciplines, and as it will help us to understand how arguments are constructed, analyzed, and evaluated. So, therefore, it is going to be important for every courses that program, especially for information technology, as you will begin to know if this statement will be either true or false, and this will be the foundations for any courses that you'll begin to take as you go through. Now, in mathematics, it is foundation for proof. Propositional logic forms the base for constructing formal mathematical proofs, statements that are manipulated with logical connectives to derive conclusion from premises. So here then, we're trying to work on with their if the statement if it's either true or false, we'll begin to check that one based on the logic actually. So in a direct proof, one starts from known true proposition, which is the axioms, and applies logical rules to prove a theorem. Of course, we're trying to work on that as we go through. We'll begin to deal with some examples pertains to that one. Okay. Now, here then, it is a foundation as well for, in terms of logical equivalence. So since there will be a loss that will begin to deal for in terms of equivalences, so it will help us to identify when two propositions are logically equivalent, meaning to say that both the left and the right side would be a little bit if they are equal to each other. So, just a moment. There will be someone who chatted me. 1 second. Okay. Now, I will say, for example, P, that is connective. We do have connective, which is the arrow is equivalent to the this not Q, then we have not P. This actually is if then. Um, if P is true, then Q is equivalent to not Q. If not Q, then not P. So that is contrapositive. But we'll begin to understand that one actually. Now, pertains to in computer science, programming is also um, programming is software development. Propositional logic is used to create conditions, loops, and functions. Logical expressions define how programs react specific input. So in programming class, it is really important because as you will begin to know if the statement, if it's either belong to true statement or false statement, learning those kind of propositional logic, you can definitely know how to map out those logic in terms of your programs. The if else statement in a program are built upon logical condition also. Say, for example, you're trying to deal with the specific loop control or statement um, operations, especially in our programming, we do have that one. The statements for if else, other the case, switch cases, it depends. If that is applicable right there, we'll begin to see as you go through, because that is the foundations for learning some logics as well. Now, in terms of circuit design, propositional logic is used designing digital circuits. Each logical gate and or not corresponds to basic logical operations in a propositional logic, enabling the creation of complex digital system. Like, for example, a circuit that turns on a light when two switches are both in the on position is based on the logical operations. And of course, since if the circuit is turned on, so therefore the light will be on. That's actually um, how does it that work? So we'll begin to understand that one based on the logic gates in the future, since we'll begin to try to walk through those logical gates. For logic gates, actually, because if you will really learn about that, that's what I have stated last time. Logic gates is something, like for example, we have like this. So for example, a point arrow, or it could be like this. It could be like that. This is something like this. This is for A, or this is for B. And the result would be, if this is the case, it could be A times B, that is for AND. If this is the case, if we have A, we have B here, that's A plus B. I'm not really confident in terms of this because we're not there in the logic gates, but I'm just just based on intuitive. If I can still remember, just correct me if I'm wrong. Then, no, in artificial intelligence, automated reasoning, propositional logic is used in AI systems to simulate human reasoning and decision making and uses to represent knowledge and derive conclusions. An expert system, a set of rules based on logical connectives, allows this system to draw conclusions from available acts. So, of course, class in our artificial intelligence, since we're trying to work on with how the system will work and how the system will begin to learn if the statement is true. Of course, you will begin to feed that into the brain of the computers, and then efficiently this kind of system of yours will gonna learn from the data that you have successfully feed it right there, and that is definitely dealing with logical connectives then. Okay, the knowledge representations here then, propositional logic helps in representing facts and relationship in a way that machine can reason about them logically, because first class, if these you're trying to let the system learn from the data sets, and then eventually learn can really behave, I mean the system can really behave if this kind of statement, if it is true or not, if this is aligned to what you are trying to ask or not, based on the assessment of those particular systems that you're trying to develop. Okay, let's move on to the history of the propositional logic. First, then the origins in ancient philosophy. According to in the year 384 to 322 before Christ era, the roots of propositional logic trace back to the ancient Greek philosopher Aristotle. who developed syllogistic logic. This is primarily focused on categorical statements such as all men are mortal and examine how conclusions could be drawn from premises. So we are trying to work on with the propositional syllogical logic. In syllogistic logic class, this is actually we have the premises, and then you will begin to work on what will be your conclusions based on those kind of pieces. And then, for example, the Aristotle logic. I'm so sorry. We're going back to the other slides. I'm sorry. Okay. Say for example, was okay, the Aristotle syllogistic logic was an early system to evaluate reasoning based on categorical statements, as it is focusing on drawing conclusions from premises such as all men are mortal and Socrates is man. Therefore, the conclusions that we can derive from there, that Socrates is mortal. Okay, that's how it worked for the syllogistic logic. The structure of syllogism. Syllogism consists of two premises and a conclusion, forming a logical argument. For example, all humans are mortal, that is the major premise. And Socrates is human, that is the minor premise, leading to conclusion, which is dealing with Socrates as mortal. Now, the differences between syllogistic and propositional logic. Syllogistic deals with categorical propositions, while propositional logic focuses on simple statement that can be connected, that can be combined using the logical operators or logical connectives. Then propositional logic allows for more flexible combination of statement with operators like and so on and so forth. There will be a lot of operators that we'll begin to learn with. Now, in terms of the Aristotle syllogistic logic, simple syllogism. Say, for example, all birds have feathers as far as a bird. Therefore, the conclusions that we can derive from that will be, therefore, a sparrow has feathers. This is how it works. Now, another history of propositional logic will be during 17th century, the rise of symbolic logic. For symbolic logic, this is actually derived, developed by Gottfried Wilhelm Leibniz, if I'm correct, 1646 up until 1716. He is actually a German mathematician and philosopher, envisions a universal language of reasoning, often referred to as the characteristica universalis. While he didn't develop propositional logic as we know it, it is his idea of formalizing logical arguments was an early step in the development of symbolic logic. So therefore, this is actually how the start of this symbolic logic, and we'll begin to work on what is those symbolic notation. So it refers to the use of symbols to represent logical operations, propositions, and relationship. It is a formal way to express logical statements, allowing clear and concise manipulations of them. So say, for example, here then class, we have the symbolic notation in logic provides a means to simplify the systematized logical reasoning by using symbols like that kind of symbols. This one. Yeah. Okay. Have or grab a specific. Okay. Therefore, this is the symbols that we're using. This is for and this is for or. And we can represent complex logical relationship in a standardized form. So say, for example, this is a structure in symbolic logic. Here, in symbolic logic, complex statements are broken down into simpler components and connected by logical operators. For example, a compound statement such as if it rains, then the ground will be wet, can be written as this one. P is actually for if it rains. Then Q is for the ground will be wet. So this particular arrow that we do have, that is for if then. So if P is actually it rains, then Q is the ground will be wet. So you will begin to quantify that as this one. If P, then Q. That's how it works. This is really going to be amazing. Now, the differences between symbolic logic and propositional logic. Propositional logic is a type of symbolic logic that focuses on logical relationship between proposition using connective like and or not. It deals with simple statement that can be true or false. And for the symbolic logic naman, on the other hand, it is a broader field that includes the use of symbols, meaning to say from the statement, we're trying to quantify that one into a symbols, definitely. So including propositional, predicate logic, and other formal system. It is not limited to propositional logic and allows for more complex forms of reasoning. And this is gonna be fantastic. Now we have here the symbolic notation, which pertains to the conjunction and the conjunction or the and, that is this symbol. So therefore, meaning both statement must be true for the entire expression to be true. The light is on, the switch is flipped. Say for example, this is the statement, and then the symbol for that one is this. So if we're trying to work on with and, so if the light is on, no, the light is on and the switch is flipped. So since and the switch is flipped, we're trying to concatenate them easily. Now for or is like a V. Now, meaning at least, I'm sorry, at least one of the statement must be true. So if that's the case, the expression to be true, the light is on, the switch is flipped. So for example, how to work on that, we'll begin to P or Q. So if, I don't know, there's no if. The light is on or the switch is flipped. That's actually how does it work. Now for negation, negation is not. For example, we are trying to refer with one statement. So if P, meaning that we have the P, for example, then the symbolic notation will be this one, not P, that represent not P. Meaning, it is, we're just trying to invert that. The negation of P, meaning if P is true, then not P will be false. So that's actually the kabaliktaran niya. So if P is, the light is on, so therefore the not P will become the light is not on. That's how it works. Now we also have the if then. As what I mentioned earlier, that the if then is represented by arrow, which is one side arrow, which is one direction. If P is true, then Q must be also be true. That is the meaning. So we have here, it rains, the ground is wet. So if this will be the representation, so therefore if you will begin, you will read, you will actually read that as if it rains, then the ground is wet. So that's actually how does that work. Now, we also do have the biconditional or if and only if, meaning to say that bidirectional ang arrow tanga symbol, this one. So meaning that P and Q must either be both be true or both be false. So the light is on and the switch is flipped. If this will be the symbolic that we're trying to work on. So if the light is on, no. The light is on if and only if the switch is flipped. So that's actually how does that work. We have here the results if you will be to try to work on with that. Now, the conditional here then, if then, excuse me, if then, for the conditional, take note that for conditional there will be unless. Unless. So notation, we have here the same representation. However, take note with the word unless. That is for conditional. If earlier we're able to work on with the other, which is the for the implication, this one. But right now, this is different because this is with unless. 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 I'm sorry. Meaning the conditional statement that with and unless interpretation, meaning if P is false, Q will definitely follow. So say for example, P, you apologize, she will forgive you for Q. So if you will read that one, you apologize unless she will forgive you. That's she wants. Unless you want her to say upset. It will be like that. So if we're trying to use if then, if you apologize, it will not gonna work. It will be different representation. So the thing here, you apologize unless you want her to stay upset. The Q will definitely be changed. So here then, for example, you go out with me for the P, then Q, we will have fun. And what will be the results for that? The result will gonna be, you go out with me unless we end up at a boring event. Diba? That's the case. Now, but anyway, No worries in that. I'm just explaining if those kind of major complicated thing. Now, exclusive or is different. We have here the symbol which is cross with a circle. True when either P or Q is true, but not both. So what I will eat pizza or pasta, like for example. So you're trying to um you're trying to refer if the statement either true. This is definitely expanded for the or operations as well. Now, for this one here, we also have tautology. We do have this tautology, P or not P. So meaning always true no matter the truth value of P. So it is raining. So for example, it is raining or not raining. That's actually the tautology all about. Now, we also have the contradiction, which is the and. So if P and not P, always false as they cannot be both true and false at the same time. So what will gonna happen? It is raining, and it is not raining. Diba? It's actually gonna be amazing. Now, we're done with the symbolic logic. We will begin to run through with the 19th century, the formalization of logic according to George Boole. For George Boole, the formalization of propositional logic began with him, an English mathematician in his work, The Loss of Thought, in the year of 1854. Boole introduced the concept of using algebraic structure, now known as the Boolean algebra, to express logical relationships. So he is actually one of the who introduced this kind of Boolean algebra approach. So for Boolean algebra class, it is a branch of algebra that deals with variables that take on binary values, which typically true or false. It is a mathematical structures that will allow the manipulation of logical operation such as the and or now, and more using symbols. Boolean algebra is used extensively in computer science, digital circuits, and propositional logic to analyze and simplify logical expression. As what I mentioned, learning about this one will definitely expand your knowledge in terms of any kind of situations because this is building or trying to develop you to become logical thinker. Now, what is Boolean algebra? For the basic element of Boolean algebra, the variables here then represents logical statement or proposition and that their values are restricted to true or false then. And their operations, these are fundamental logical operations that work on Boolean variables like the and or not or x or whatsoever and so on and so forth. Then for common Boolean algebra operators, this is definitely the same with the symbolic operators. The and operation returns true if and only if both operands are true. Take note of that. So example, if it is raining, I don't know, if P is it is raining and Q is the ground is wet, therefore P and Q means it is raining and the ground is wet. It is the same with the symbolic logic, however, here is statement. Now, or operation, meaning the or operations returns true if at least one of the operands is true. So if P is I will study and Q is I will watch a movie, then the result P or Q means I will study or I will watch a movie. That's really so simple. Now we also do have not operation, the same with the symbolic logic. The not operations inverting the truth value of the operand, meaning it is, when we say operand class, that is the letters, that is any value, any statement or whatsoever, okay? The operator is the plus, minus, times, and so on and so forth. The not operations inverts the value of the operand, meaning if the statement is true, it becomes false. And if it is false, it becomes true. That is kabaliktaran. If P is the light is on, therefore the answer will become the light is not on. Now, for XOR, exclusive OR, operations returns true if only one operand is true, but not both. So if P is I will go to the party and Q is I will stay home, then P plus Q will definitely derive as I will either go to the party or stay home, but not both. That's how this common Boolean algebra operator works. Now, afterwards, we also have here the implication operations, meaning the implications operations representing a conditional statement. If P then Q, it is false only if when P is true and Q is false then. So if then We're trying to work on with if then. So if P is it rains and Q is the ground gets wet, so therefore the value for this one, if it rains, the ground gets wet. That's actually so simple. Now that we have the biconditional, the same with the symbolic logic, actually they are related to each other. It's just that George Bull were able to expand that with statements. So the biconditional operations meaning, because in symbolic logic, we're referring to the symbols only. But here then, we're trying to quantify specific statements. Now, the biconditional operations means that the both sides of the statement must be equivalent. Both P and Q must either be true or false. Say, for example, if I will study and for the P and I will pass the exam for Q, so for their result, I will study if and only if I will pass the exam. That's actually the representation. Now, let me drink water. Okay. NAND, we also have NAND operator. Notation will be a peer, not or net end. That is not end. So meaning the NAND operation is the negation of the AND operation. Meaning, excuse me, it returns true except when both operands are true. So for example, true plus true and true will become true, di ba? Now, meaning it returns true except when both operands are true. That's actually how this works. Now, ang both operands are true class sa times natin din. True times true will become true. But it will return true except when both operands are true. Since this is the AND, of course, we're trying to negate that it will become false. Meaning to say, what will gonna happen for that? True and true, for not AND, it will become false. But of course, it is better if the result of true and true, since that is quantified as true, you will just negate this, will turns to false. That is really so simple. So if P it is raining and Q it is the ground is wet, then the NAND result for that will definitely, it is not true that it is raining and the ground is wet. That's how it works. Now for NOR, or not OR, this is not an OR cubes. So P not OR Q, meaning NOR operation is the negation of the OR operation. So we're negating the OR operation if in calculation. So if true plus true false, for example, that will become false. So, no, true. So therefore, it will become false for the NOR because we're trying to negate this. That's how it works. Now, if false plus false, that is actually being quantified for OR as false. So therefore, it will become true for the NOR. So meaning it returns true only when both operands are false. This one. That's how it works. That's the meaning. So hopefully that's clear. If P is I will study and Q is I will watch a movie, then the NOR means it is not true that I will study or I will watch a movie. Excuses. Excuses. Now for X NOR or the exclusive NOR, it is the negation of XOR. Meaning it returns true when both operands are the same, both true or both false. So XNOR is the negation of the XOR. Let's try to quantify. If OR is 3 plus true false will become true, and then the XOR and a NOR is the negation, right? The negation of the OR operation will become false. So the negation of XNOR will become true. This one. So if F plus F for OR, it will become false. But for NOR, it will become true. But for XNOR, it will become false again. So meaning they are equivalent, XNOR and OR. So meaning it returns true when both operands are the same. both true or both false. So that's how it works. If P is I will go to the party and Q is I will stay home, um, then I will go to the party if and only if I stay home. That's the process. Now let's actually work on. No worries on the calculation. I will begin to give differently for that. Now for the tautology, we also have here. We have here P and not P. A tautology is an expression that is always true no matter the truth values of the variables. No matter what will happen, class, this can true plus true and true. I don't know. True plus true or not true. 2 times not true, that is false. It will become false. True and false. True times the false. It will become still true. That's how it works. If you're trying to work on with false, then not false. And that is true. False times true will become still true. That's how it works here. So it is raining. Symbolic expression P and not P. It is either raining or not raining. Oh, no, sorry. This is or. This is plus. This is not times. Sorry, correct. So if true plus false class, kung sa or operation natin, true plus true will still be true. Then false plus true will still be true. The same that in here. True plus not true is true. And false plus not false is still true. That's how it works. Now for contradiction, regardless of what will gonna happen, a contradiction will always be will always be false. Meaning to say this is multiplication because this is and. So like for example, true and not true equals quantified as false. Why? Because in and, true, and this is false. Actually, not true will become false. So true times false, it will become false if you know the process of the and operation. So it is raining. Our P, it is not raining, and it is not raining. That is, it is both raining and not raining. If you will begin to work on with the statements. Now we have law of Boolean algebra. This is the equivalences in our propositional, but we'll begin to really discuss the propositional equivalences in different situations also to really expand your learnings. Now, for laws of Boolean algebra class, it is actually P then and Q is equals to Q and P. And P or Q is equals to Q or P. Regardless kung ano ang i-calculate mo di una, they are still be equal. And the commutative law states that the order of operands does not affect the result of the logical operations. This applies to both and or operations. Say, for example, you're quantifying, this is P, and this is Q. So, true plus, true and true, this is times for and, this one. So, true and true, false, na lang. True and false, the result will become false. If Q naman unahon mo, false times true, it will still be false. That's how it works. But if plus, true plus false, we all know that the true plus false is still be true. If Q start false plus true, it will be still true. That is equivalent to each other, right? Now, for commutative, for and, it is raining, the ground is wet. For commutative class, it will equals to P and Q not P. Meaning to say, if you're quantifying P times P, so it will become true. But regardless, Q to 2, true to times 3, it will always be true. That's why they are equal. It is raining and the ground is wet will always be the same. The ground is wet and it is raining. Post a statement. And for or naman, I will go to the movies for this one. The result will, I will study and I will go to the movies, and that is still equal. I will go to the movies and I will study. That is really so basic. And for associative law, the associative law states that the grouping of operands does not affect the result of the logical operations. This law applies to both and or operations. Meaning to say, class, this is either, since in our law, precedence rule for calculation in mathematics, we have the PEMDAS. When we say PEMDAS, that is parenthesis first, exponential, multiplication, division, addition, subtraction. So we can start from here and we can start from here, for example. Regardless kung diin ang iuna mo di, this statement, you will calculate this one and you will calculate this one also here. I mean this one. They are still equal. So say for example, we have through, we have P, we have Q, and we have R. So false and true, say for example. Now, we will use this first. P or Q or, and, that's R. That's and. When and is multiply. Okay? Now, true times false, because we will work on with the parentheses. P and Q, true and false, it will become false. And false, the result from here will be this. False times true is actually false. Still, the result. So let's try to see, this is the answer for this first one. Let's try to see if this will gonna work, will gonna be equal to false still. Now, Q times R first. Q times R, false times true will be false. So this is the result for Q times R. Multiply that into the P. False times true, it will be false. So meaning they are equal to each other. That's why that is associative. The same with or for plus. If P or Q, true plus false, it will become true. Then plus or plus R, true plus true will be true. So the result is true. Let's try to work. This is for this one. This is true. Let's try to see if this statement will be true. So we'll calculate Q or R first. False plus true will be true. True plus P, that is true, plus true, that is true. So they are equivalent to each other. They are associative. Now, in a statement, it is raining, the ground is wet, and the grass is damp. So it is always equal class. Using this here, P and Q, then and R, it is raining, the ground is wet, and the grass is damp. So it is still equal if here then they were able to quantify this one is still B, it is raining, and the ground is wet, and the grass is damp. It's still the same as is. For associative, this is or. So I will study, for associative or, I will study, I will play video games, I will watch TV. To quantify that one using this, it will become I will study or I will play video games and I will watch TV. The same here then, I will study or I will play video games or I will watch TV. They are equal to each other. They are equivalents. So that's how it works. Now for distributive, this is the same. You will distribute this one here, this one here. That is P, this is and over or, diba? And over or, and this is and over or. This is or over and. So let's try to quantify if they are correct. So distributive law allows us to distribute an and operation over an or operations and vice versa. That will enable simplifications of complex Boolean expression by distributing one operations over another. Say for example here then, for P or Q, let's try to, calculate P, Q, R. So we will begin to work on with Q or R first. We have this. So Q or R, well, when we say or, that is plus, diba? So true plus F, that is true. Then that is and times and, true times false, that is true times false will become false. That is how it does work. Now, let's try to see if the answer here will equates to false. Now, P and Q, false and true, if it is what? That is false. And we have here they P and R. We have P false and false, it will become false because multiplication for N. Now we have OR. False plus false, it will become false. Therefore, they are distributive equivalent. Now, for P or Q or R will be the same thing. But for example, we have Q and R here. Q and R, we have true times F, that is false. False or, that is or plus false plus P, that is false, that is still be false. Let's try to see if the answer for this here will be false. P, and that is or, P plus Q, false plus true, that is false plus true, that is true. Tapos, P and R, false plus false is false. So we have and true plus true times false, it will become false. So therefore, they are equivalent. So that's how it works. Now for distributive law, for and over or, I will study and it is raining or the ground is wet. That is how it works. And for this one here, I will study, and for this here, okay ha? Ato na. Q or R, it is raining, the ground is wet. Afterwards, you multiply that here. It will become, I will study and it is raining or the ground is wet. So, okay na, calculated. So for P or Q, it will become and Q, that is and. So it will become P and Q, I will study and it is raining. Okay? So we have P and R, I will study and the ground is wet. So we have or. Take note. So earlier, I will study and it is raining. Then I will study and the ground is wet. So therefore, I will study is actually double. What will gonna happen? It will become, I will study and the ground is wet. So mag-or taya in between. Kagina. So I will study and the ground, I will study and it is raining or the ground is wet. This is not, gakatalang na ta. 1 second. Let me correct that one. The one that I'm referring to is not and. It is or. This is for or. Right? No. This is and. Correct. And this is or. Sakto to answer natin gali. I'm so sorry. So I will study una and it is raining or the ground is wet. That is still equivalent to I will study and it is raining or I will study and the ground is wet. To simplify that one, I will study and it is raining or the ground is wet. So let's try to see. I will study and it is raining or I will study and the ground is wet. That is still the same. Because doble siya ho. I will study and it is raining. So doble na I will study. So therefore, remove this siya. Because one man, naman, ikadua na siya, so makancel siya. So if we cancel na siya, to simplify, I will study and it is raining, or or the ground is wet. So therefore, the same na siya sa babaw. That's how it worked then. Hopefully that's gonna work for you. Now, here then, this is or, and this is and. So what will gonna happen? I will study, or I will play video games, and I will watch TV for this one. Now for this here, I will study or I will play video games, and I will study or I will watch TV. Since I will study is redundant, we can omit that one. I will study, tapos, or I will play video games and will watch TV. It's right to see. Yeah, that's correct. I will study or play video games, and I will study or watch TV. So remove this one. So I will study or play video games and I will watch TV. It's fine. That's how it works. But it's okay lang kung wala ni mo gisacrifice. That's okay. Now, for this one here, for identity law, it is this one. We have P and true. So if P times, if P times true, it will always be P. And if P or false, it will be always P. So P times true, it will always be P. Tapos, P, or man siya, di ba? This is or, V, on a plus. If plus false, it will become P. So the identity law states that when an operand is combined with a true value using and or a false using or, the result is just the original operand. This law helps simplify expression when combined with truth values. Say for example, class, if ikaw ni siya si true, tapos i-multiply ka sa true. So true times true, you will always be true. Diba? Now, if ikaw naman is si P, tapos ikaw ni si false, no, I'm so sorry, true. If ikaw naman is si true, plus ka sa false, you will always be true to yourself. Amo na siya. Diba? Kuha? Hopefully that's clear. So for example, for and with true, it is raining, plus true. So, and true. So therefore, it is raining and it is raining. Diba? It is raining and true. It's just, it is raining. Alangaman, it is raining and it is raining. So it is raining only. Because you are trying to combine itself. And then, or with false. So I will study or I will study. I will not study. So they, in our plus, true plus false, the true will be the highest precedence. So I will study ang result niya. I will study or false, it's just I will study. So therefore, this is I will study. Now, we also do have the complement law. For complement law, we have the P, tapos and multiply with not P is equals to false. And P plus with not P equals to true. The complement law states that the statement and with its negation is always false, while a statement or with its negation is always true. This law helps eliminate contradiction in logical expression. Paano na siya go-work? Say for example, if P is true, tapos N is not true. So not true will be simplified as false, di ba? True times false will become false. Because in our AND operation, multiply true to false will always be false. True times not true will be false. That's how it works. Now, for or, so true plus not true. So this not true will be false. So true plus false is always true. True plus not true is always true. So that's actually the logic. Now, say for example, for and with complement, it is raining, and the not P is it is not raining. So the result for that one, it is raining and it is not raining, is always false. What will gonna happen? The answer for that, it is raining and it is not raining, so the answer is just simply false. So the complement law here If you're quantifying that it is raining and it is not raining, the answer will be false. And what is the false statement? That is, it is not raining. Okay? Now here then, or with complement, it is sunny or it is not sunny will always be true. So it is sunny or it is not sunny is always true. So therefore, true statement, it is sunny. So it will be, it is sunny. Okay? Now for idempotent law, it's hindi siya idempotent, idempotent law. So it is P and P is equals to P. So that is true times true is always true. Tapos if true times a plus true is always true. That's how it works. Diba? That is reflecting to itself. Law state combining statement with itself using either or does not change the original value of the statement is well. Simplifying expression in the same variable appears multiple times in a logical operation that will. Like I said, reflection ng self. So if it is raining over the end, so it is raining and it is raining will always result to it is raining. Now for the or I will study will always result to I will study. Now we also have the De Morgan's law. Now for De Morgan's law, we have the not over the P and Q. So therefore, P and Q will calculate that one. If we have true times true is equals to true, then you will negate that, it will become false. Man. Tapos, ang equivalence niya is amuni siya, not P. So, true, ang not true will become false. Ang not sang Q, which is, this is P, this is Q, okay? Ang not sang Q will be false. Tapos, may end. False times false will become false. So, therefore, they are equivalent. And very good. Now, for this here, for the or, so P plus Q. So if P plus T will always be true. Tapos, ang negation niya, negation of true plus true will be false. So what will gonna happen? Not P is T will become false. Not Q is T will become false. False plus false is always false. So therefore, they are equivalent to each other. So that's really so simple. Even 5 months inside the womb of their mother can answer that. How about you, that you're actually first year college already? Hopefully that's you're actually learning from this. This is absolutely total logic. So the Morgan's law provides rules for negating a conjunction or disjunction. This laws allow us to simplify expression involving negation and logical operation. I know, class, this is totally lost, but really familiarize this because I don't want you to have low score from this lost laws. Anyway, just it's not funny to but we have to be serious. Yeah, this is not a joke since this will relate to your grades. At least you will learn something from me, diba? So De Morgan's law for and with a statement, So if the statement, my pita, it is raining and the ground is wet. So using this one, so we have to quantify this. It is raining and the ground is wet, but we are using not. So it will become, it is not raining and the ground is not wet. It will become like that. So here then, not P. It is not raining and the ground is not wet. So if you are trying to work on with this, it is both not raining. It is both not raining and the ground is not wet also, diba? Either it is not raining or the ground is not wet. They are equivalent to each other. But you were able to understand that. For or with negation naman, here then, I will study or I will play video games, but there will be not. I will not study or I will not play video games. Here the same thing. I will not study or I will play video games. That is really so simple. Now, for the difference between Boolean algebra and propositional logic. So Boolean algebra class formal system focus on the manipulations of binary variables using algebraic operation. But for the propositional logic, a part of logic that focus on statements that are either true or false and examines the logical relationship between them. Take note of those. And for the application, Boolean algebra used in fields like computer science, digital circuit, and simplifying logical expression in terms of gates. When we say gates, amo na ni siyang mga amo ni katong ginhambal ko previously. Mga drawing that you will definitely have a good drawing. The application for propositional logic used in logical reasoning, proof, and deduction. And we also have here the values deals with binary true or false for Boolean algebra, but for propositional logic, we're also dealing with focus on proposition or statement that can be true or false. And for the operations involved not, or, and, so on, here then for operations of propositional logic, or, not, if, then, and so on and so forth. However, they are actually have the same operations, values. I mean, how to calculate that one, the same pamagyakan. And for Boolean algebra is more algebraic and focused on manipulating truth values and simplifying logical expression using algebraic methods. And for propositional logic is concerned with the formal logic reasoning process using statement and connected to perform values and conclusions. For propositional logic, ang mga sentential ang ating ginafocus. So here then, we have the Boolean algebra examples. For AND operation, returns true if both P and Q are true. It is raining, the ground is wet. So it is raining and the ground is wet. So the table will be this one. We have true plus true, it will become true. True plus false will become false. That's not plus. True times true equals true. True times false will become false. False times true will become false. False times false will become false. If we're trying to learn with that with numbers, 1 times 1 is 1. 1 times 0 is 1. No, 0. 0 times 1 is 0. And 0 times 0 is definitely 0. That's how it works for AND operation. Now for OR, returns true if at least one of P, at least one of P or Q is true. I will study or I will watch a movie, I will study or I will watch a movie. So true plus true, it will become true. True plus false, that is true because at least one. False plus true will be true. False plus false is false. Of course, that's false. Now, if 1 and 0, 1 plus 1 is equals to 1. 1 plus 0 is equals to 1. 0 plus 1 is equals to 1. And 0 plus 0 is equals to 0. Reminder that 1 signifies true and 0 signifies false. Okay? 1 plus 1 is not 2. That is not 1, ha? That is true. That is not 1. That is not 2, ha? The 1 plus 1 here in our discrete mathematics, 1 plus 1 is definitely 1 because that's how it works. It's totally funny, but of course, that's how does that work. Not operations invert true value of P is true. If P is true, then not P is false, and vice versa. So the light is on will become the light is not on. Say, for example, you have true, it will become false. If you have false, it will become true. If you have 1, it will become 0. If you have 0, it will become 1. That's how it works. So for XOR operations, return true if when exactly one of P or Q excuse me, returns true. Excuse lang, anay ha. Returns true when exactly one lang ha, of P or Q is true, but not both. So I will go to the party, I will stay home. So I will go to the party or stay at home, but not both, of course. So what will gonna happen? True plus true is not only 1, so it will become false. True plus false is only 1, so it will become true. False plus true will be, that is plus, ha? False plus true will become true. False plus false is false. This is different with OR because OR is at least 1, but here is exactly 1. So for 1 plus 1, For exclusive OR, it will become 0. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. That is real. That is basic. Now for NAND, it is not AND. So from the word not AND, ang result sang AND kagina, gin-negate taya, gin-invert. So it returns false only when both P and Q are true. So meaning, for our AND kagina, it could have been better that you're trying to get the AND. So true times true, it will become true. True times false, it will become true. False. False times true will become false. And false times false will become false. So what will gonna happen? It returns false only when both P and Q are true. So both P and Q are true. So sang AND natin, this is for AND. So true will be the negate function result will be false. False will turns true. False will become turns to true. False will becomes to true. That's the logic. Much better to get first the AND for you to negate simply the AND into NAND. Excuse me. Hopefully you were able to get that one. Now for not or, it is the negation of the or operations that returns true when both P and Q are false. I will study or I will go to the movies, meaning it is not true that I will study or go to the movies. That's basic. Say for example here then, it returns true only when both P and Q are false. So paano siya? Ang not or is just the negation of or. So ang or kagina, true plus true is true. True plus false is true. False plus true is true. So false plus false is false. Now, the negation. True negation is false. True negation is false. True negation is false. False negation is true. That's how it is working. I know, that's how it works. Sorry for that. Absent-mindedness, sir. Now, it is really so simple. Hopefully, you were able to get the logic behind. Now, we also have the exclusive NOR. For exclusive NOR, it is the negation of XOR. XOR earlier is the exclusive OR. Meaning, ang true plus true, exactly one malang ang true. Diba? So, true plus ang exclusive OR kagina. No. This is not. Exclusive OR, this one, right? So, true plus, true times, NOR is plus. So, 2 plus true, that is, let's verify the XOR, huh? Yeah, that's that one. This is exactly 1. Now, let's try to prove. Here, true plus true is false because not exactly 1. True plus false, exactly 1, true. False plus false, true, that is true. False plus false is false. Now, the negation. False will become true, true will become false, true will become false, and false will become true. Now, returns true when P and Q are either both true and both false. So, true and true, true. False and false, true. That's basic. But it's better that you were able to get the function for the XOR. For the XOR. Now, for implications, this is for if-then. So, operations for if-then, P, if P, then Q. So, it is false only when P is true and Q is false. P is true, then false. Amo lang ni siya. So, the ground is wet. If it rains, the ground will be wet. So, what will gonna happen for if-then? So, true plus true is still true. True plus false is false because of the law here. Now, false plus true, true, false, false, false will be true. Now, for biconditional, this is biconditional always true. If the P and Q have the same truth value, both true and false. Meaning to say true plus true will be true, false plus false will be false. True plus false is not the same, so that's false. False plus true, that's not the same, will be false. I will study and I will pass the exam will be true. I will study if and only if I pass the exam will always be true. Now, the tautology. Tautology is an expression that is always true regardless of the truth values of the operand. It is raining or not, or it is not raining. Say, for example, true, then the true value for not P, we have P, the true. The not P for true will become false. Diba? Now, true, this is or, diba? So, true plus false will become true. Then false. Then ang false niya nga ang function, I'm so sorry ha, kay hindi na siya true diho, that is false supposedly. So begin to change that in the presentations later. Take note, page ano. Page I will just edit that in my presentation before attaching that into you so that you will not begin to so that you will really learn about that, okay? Now, so false, you have false for the P, not P. So, ang equivalent sa not P is true. So, false plus true will become true. So, that's how it works. Now, we also have here the contradiction is an expression that is always false. So, here then, class, if P is true, then ang not true, sang true will become false. Supposedly false, maybe, ha? So, true times true, because this is man. True times false will become false. False, if P is the false, then not P is not false, it will become true. Negation. False times true will become false. That's why. That's actually the function. Now, the history of propositional logic. Logic gates are fundamental building blocks in digital electronics and digital computing. They are used to perform logical operations and binary variables. These gates manipulate binary input, true, false, 1 or 0 to produce a specific output. Logic gates are essential for creating more complex circuits like adders, multiplexers, and memory storage element. So we will deal with logic gates. But for logic gates class, we will not include that in prelim term. We will just work on that with the midterm term. Okay. Logic gates are the fundamental components in digital electronics and computing. They perform logical operations on binary variables, forming the backbone of modern digital devices like computers, smartphones, and microcontrollers. Amo ni siya gina-learn natin in order for us to really learn about the certain how the flow or the logic will really work. I'm sorry. Okay. Early 20th century, the expansion and precision. Bertrand Russell and Alfred North Whitehead. In the year 1910 and 1913, Russell and Whitehead expanded upon French's ideas and published the Principia Mathematica. This massive work aimed to ground all the mathematics in formal logic. They formalized much of the logic that Boole and Frege had begun, but also highlighted the limitations and nuances of propositional logic. So they were able to improve the formal logic class in this time. And for the mid-20th century, say Gödel's, the Kurt Gödel, 1906 up until 1978, made a groundbreaking contributions to logic and mathematics, particularly through his incompleteness theorems. This theorem showed that no logical system could fully capture all truths of arithmetic, which had deep implications for the scope and limitations of propositional logic and formal system. So this is actually a bit of complex because Gödel's work indicated that propositional logic, while useful, is not capable of proving every truth in mathematics. That's how it works here. It's complicated, but completeness and non-completeness is definitely a bit of challenging, but hopefully it's part of discrete mathematics, but it is too broad. Pretty much you will begin to deal with that with algorithms and complexity, data structures, so far. So mid-20th century class, logical systems and computations, Alan Turing, this is for automata already, which is Turing's development of the Turing machine, and the idea of computability was influenced by propositional logic, his work showed how logical operation can be modeled by a machine, which is the foundations of modern computation. That is for automata class, which is having the true and false also with the input tape, the true or false. What if we begin to input the certain criteria of one where it leads to true or false statement, for example, like that. You will begin to learn that in automata if you will be under with me if you're computer science then. Now, the growth of computer science in 20th century, Boolean algebra and computing with the rise of digital computers in the mid-20th century, Boolean algebra, which forms the mathematical foundations of propositional logic, became crucial in the development of digital circuits and computer logic gates. So it has transformed a world-wide useful katama ang modern computing in this era. We're able to improve and develop a certain improvement and development in our era. Now, 21st century applications in AI and formal reasoning. Artificial intelligence has been developed. Propositional logic remains vital in automated reasonings and decision-making systems. Logical operations are used in knowledge representations and decision trees to model intelligent behavior. This is how does that work. We'll begin to transform that. Actually, if you will learn from AI, it is definitely in AI course, you will deal with more broad cases and implementations of true or false. Especially more on heuristics na and calculations of mga pretty much calculus and differential. So applications of AI and formal reasonings, computer science and software development, propositional logic continues to be foundational in fields like software testing, automated theorem proving, and cryptography, where logical operations define the correct operation, security, and data integrity. So that's why it is really good to know the foundations here in our discrete mathematics for you to apply this in wide application. Now, the applications of propositional logic, programming and algorithms is essential in the design, if, then, statement, loop, and decision trees, which are the foundational to programming, and that will ensure that decisions are made based on the truth values of logical conditions. So this is really the usage wherein we can apply this propositional logic when it comes to the algorithms and programming. And digital circuit design also, since we have the logic gates, each digital gates and or not and so on directly corresponds to a logical operations and propositional logic, which engineers use propositional logic to create circuits that perform specific tasks, such as adding numbers or controlling devices. So that's why learning with these cases is really important for you to really perform a good result. AI and knowledge representation. In AI naman, propositional logic help machine simulate reasoning by structuring information, applying logical rules. This is used in decision-making system like expert system and automated reasoning software. Of course, plus if we're working with GPTs, with summarization, sa NLP, you're trying to work with decisions still. And for mathematical proof, propositional logic is to prove theorem through direct proof and direct proof, contradiction, and logical equivalences. It helps in simplifying complex statement into more manageable form. That's why it is really important to learn this propositional logic. So that's the end of our discussion for the propositional logic, and I'll be going to discuss with the connectives and then logic table, then calculation, then the equivalences in the different videos. Thank you so much, everybody. Hopefully that you learned something from me, and make sure to put a 5 sentences comment of what have you learned in this video in the comment section, and put your last name and then your takeaways, and then the section, of course, so that I can add a plus point in your quizzes as well. Thank you so much, class, for tuning in, and you can share this into your other friends if they are learning discrete structures. Thank you and good